Now let's talk about these two classical and I would say major class of design strategy and design concept, both in terms of instruction set architecture and also processor feature from hardware and compiler perspective. They are called CISC and RISC, complex instruction set computing system and reduced instruction set computing system. So these are the acronym for that those terms. Okay, and I refer this as a clash of titans. The whole world is divided into these two school of thought. Either CISC, complex instruction set computer or computation system, RISC, reduced instruction set computers or computing system. And they have their, each of them, CISC and RISC, has their own philosophy of how a processor should be constructed. Okay, so CISC philosophy is to reduce the amount of memory usage and access. I'll kind of try to compare it with the RISC and in terms of CS147 DV of each of this point. So reduce the amount of memory usage and access. What is meant by that? So if you recall, we have this example, this simple high level instruction A equals B plus C. How it is translated into our CS147 DV is that you first access memory corresponding to the variable B and correspond to the variable C, which is basically two load word, right? And then you add their content of those. So load word basically will read from the memory and store it in certain register. Now you add values of these two registers, that is the third instruction, and store it in another register in the register file. So that's add. So two load word, one add, and then a store word from that result containing register into the target memory, which is belongs to, let's say, variable A. So one simple instruction contains like four simply high level instruction A equal to B plus C that is implemented through machine code with four assembly level instruction, two load word, one add operation, another store word operation. That means each of this instruction is like 32-bit, 4 byte. That means to achieve this A equal B plus C in the high level, we need to store an instruction in 32 bytes, like 16 byte. Each of them is 4 byte. So total 16 byte of space you need. Now think in the other way, right? Here I am accessing these two memory location from two addresses, right? Then adding, then storing. What if I use some sort of instruction format and strategy where I use direct operand access, direct addressing method, as we just learned in previous couple of slides, means my operation itself contains information about those operand addresses, like it contains address of B, it contains address of C, it contains address of A. Then with one single instruction, it is possible to construct a piece of processor that will go look at this machine code, access address of B and C with one single instruction, right? Access those two address, add them, and store it back to the target address for variable A, right? So we are achieving just with one single instruction in that case, right? So that means we are actually, instead of storing four instruction, which is 16 byte long, we possibly can have less amount of memory to be stored for that one single instruction, which is a bit complex, right? That's what we call it, a complex instruction, right? That's the keyword, that's the buzzword, right? So that means we are trying to optimize on the amount of storage needed for your machine code. In a sense, you are reducing the amount of memory usage. Remember, your text or your machine code is also part of memory storage, right? You load it in some part of the memory and consume that memory. So CISC, complex instruction set computers philosophy, is to reduce that part of the memory. Okay, and this specific example of course give you this next bullet point obvious, which is like support complex assembly language, right? Support complex assembly level language means instead of like breaking down a simple task like a equal b plus c into 4 different instruction, to load word, another add, another store word for CS147 DV, we kind of are proposing a complex instruction format where we are embedding the addresses of these operands directly onto the machine code. So we are kind of trying to support more complex assembly functions or languages. Another target in that days, like especially just to mention, CISC is kind of, it started a computing system with the CISC style of approach. And that means it has to have a different compatibility support, different generation supports different addressing modes. So that problem is there, but that's kind of an historical problem. Now, with the same example of a equal b plus c, in this new proposal where we are embedding these variables address directly into the machine code and making just one single instruction, that means you can well imagine your compiler job become easier. Compiler job is to convert your high level language into assembly level language. So here if it says a equals b plus c, then it will go straight using that complex instruction we just developed, that one, and replace that statement. But for the other way, CS147 DV, if we think of that way, the corresponding compiler, if it sees a equal to b plus c, it has to generate like 4 machine code for that one high level instruction, 2 load word, 1 add, another store word. So this makes compiler jobs little harder. So CISC target was to make compiler's job easier. The first point, the reduce amount of memory usage and access, this is the most important point to differentiate from CISC and RISC. And in early days, it was needed because amount of memory storage was really limited in early days, right? Even if you go 10-15 years back, right? You don't, not 10-15, actually it is more now. We are 2019. I'm talking about 1980s and 90s range. We didn't have much bigger memory, right? Right now you can just go in some Radio Shack or Fry's Electronics or some other electronics component or Amazon even, right? You can go and buy like memory card of 4 GB, 5 GB memory card, no problem, right? And also hard drive storage, it can goes up to terabyte, multi-terabyte even nowadays. So memory is not a problem nowadays, but back 80s, 90s, memory was really a problem. There's no good technologies to make bigger memories. So people need to be really conservative about the memory access, and that's why CISC philosophy was kind of dominant philosophy, and everyone tried to reduce on the memory usage of any computing system, and that's the philosophy behind the CISC. Whereas RISC, reduce instructions at computer, it basically runs on the philosophy of keeping design simple. Okay. First of all, execute in one instruction per clock. You can well imagine relate this to your CS147 DV, where we are actually accomplishing each of the instructions almost like at least if it is not one clock, in that sense it's a 5 clock, but it's a constant amount of clock, like 5 stages, 5 clock, and each instruction, no matter how big, how small instruction, it will be done in 5 clock cycle, right? So it started with one instruction per clock, that kind of philosophy, and then people go with, okay, I can go with a 5 clock cycle because that makes more sense, and so on and so forth. Second is keep all the instruction of the same size. That means CISC didn't have that. CISC can have multiple length instruction. Your push in CISC philosophy, your push pop, that CS147DB, that 2 instruction will have just 6 bit of machine code. Whereas that complex instruction we just talked, A equal to B plus C, where all the operands memory addresses will be embedded in the machine code, that will probably have like many more bytes, maybe like itself it's 8 byte or 10 byte long, one instruction, right? So for CISC it doesn't matter, it basically don't want to keep instruction of the same size, again just to make utilization of the memory in most useful way, right? Example, like shift instruction in our case, like CS147DV, which uses this shift amount field, but in that case we don't use the RT field, whereas non-shift instruction, R-type instruction, doesn't at all use the shift field. That 5 bit is kind of useless for them. So in CISC philosophy, that's a wastage, right? So it will try to compact that number of bit usage there, but RISC doesn't care. RISC says, okay, I'll keep all the instruction of the same size. Basically, this second point has very important implication on the first point, because if we assume we have a fixed length instruction format, that will keep our digital circuit simple enough to make sure that at least we can achieve each instruction, we can guarantee each instruction is or can be executed in a constant amount of clock cycle, if not one, like 5 clock cycle at least, we can done with every instruction, we can guarantee it. And one of the criteria to achieve that constant amount of time for execution is keep the instruction of the same size, because in that case we know each field coming from each field serving what type of information, where from we can draw the electrical line connected to the register file. Just look at your lecture 11, like that what made the circuit very simple. Think if you want to change that CS147DV with having some complex instruction set philosophy, where you want to have a dynamic size of instructions, how are you going to manage in the hardware level? Think that way, okay? And also RISC philosophy, keep the memory access with minimum set of instruction. Dedicated instruction, load and store, either it can be load word, store word, just for our case of CS147DV. In other cases it can have load byte, store byte, load half word, store half word, that kind of instruction. But it's only limited amount of instruction that can access the data memory. Everything else is register file bound, okay? So essentially that means its philosophy is to give complex functionality, example A equal B plus C, that support through high level language. So instead of processor supporting that kind of instruction directly, where memory addresses are embedded within the machine code, it basically kind of shifted that problem towards the compiler. So it makes the compiler a little complex, which says if you say A equal to B plus C, you need to do at least this 4 operation, 2 operand access from the memory, then add and then store it back in the memory. So that that kind of complexity is kind of shifted towards the software world, making the hardware design simple. Now you can say what is the significance of doing it RISC, because it is not helping us first of all on the memory, because now we are having bigger code size, machine code size of the program becomes bigger than a complex instruction set computing system. And then also you're saying that for one instruction A equal B plus C, we are executing 4 instructions, right? Where CISC will need to execute one single instruction. So where is the advantage, right? We are definitely increasing the memory usage, and apparently we are increasing the number of instruction as well. What is the advantage? The advantage is this, that since we made the digital circuit simple, and we guaranteed that each instructions are executed within a constant amount of clock cycle, if not one clock cycle, then each of the individual instruction, load word, to load word, add and store word, it is so fast that it will have a performance advantage over complex instruction set, which tends to be slower, because it try to give the compatibility support. So it needs to include lot of different addressing mode. It need to decide on fly how I am going to access the complete machine code, and so on and so forth. That circuitry itself becomes so complex, it slows down the computer in that sense. Okay, so apparently even apparently RISC is increasing memory usage. RISC is increasing number of instruction per one single high level instruction. Its advantage is in the simplicity of the digital circuit, which makes it possible to run faster at each instruction level, and which will outsmart and outcompete CISC instruction set. That what happened in 90s. Like Intel was dominant in the market from the very beginning in the processor market, which is basically x86 kind of processor, and everyone followed that philosophy. When those two gentlemen, Patterson and this other one, like the one you are reading the book about, Hennessy and Patterson, right? Hennessy and Patterson. These two gentlemen proposed this RISC, and it is very interesting to read their first paper on the reduced instruction set computer. That type of proposal they make at the beginning of the 90s, that this kind of machine, and they showed it statistically, it will actually achieve faster performance than any CISC machine. And then gradually our focus in the 90s shifted towards the RISC, because in the 90s and late 90s, your memory technology was kind of making improvement, and it actually can give larger and larger amount of memory. So memory was not a very concern in that period. And then you are doing the RISC style can have a performance advantage, and that's when Sun Microsystem, that is one of the prominent company, was dominant in this throughout the 90s for all the web services and stuff like that. They followed reduced instruction set computing architecture philosophy. Okay, so towards that, like throughout this 90s, this RISC dominated. Now what happened towards the, like after 90s, late 90s, like when these handheld devices came in the market. So handheld device can have only host certain limited amount of memory at that point. Like nowadays it can host like 64 GB, 128 GB together on one devices. But back in 10 years back, if you go to 10 years, 15 years back, one handheld device like simple PDA can have what maximum like 250 megabyte or 512 megabyte, that kind of memory it used to have. So that means to support the handheld devices and mobile devices in that era, 2000 era, people again swing to the CISC, because CISC philosophy was to reduce the amount of memory. So your handheld devices has this memory. So in that point, your x86 or frankly speaking, it's an ARM technology. There is another type of processor called ARM that gets dominate over, because ARM philosophy is the same as a CISC, and it try to reduce the memory footprint. Right, so it swings there. Nowadays, it has like more memories now. Like we can have 128 GB easily on a handheld smartphone, and people are kind of swinging towards the RISC. Okay, MIPS is one of the processor, not widely used, but it used in the it has a pretty decent market. The other processor that's there onto which uses this kind of philosophy. In fact, interesting part is this. Nowadays, modern computer uses a philosophy which follows probably partly CISC, partly RISC. Even Intel Pentium, right? They claim in the market they are complex instruction set computer, but internally they are following partly RISC philosophy as well to boost up their performance. Okay, so it's kind of a mixed design trend right now. It all depends on which market segment you are targeting, what kind of problem you are solving, etc., etc. Different factors comes into place, and you pick up your optimized strategy of processor design. You don't follow blindly a school of RISC or school of CISC nowadays. But these were the major actually things 10 years, even 10, 15 years back, like CISC versus RISC. Now these boundaries are kind of blurring together and people have started compromising and stuff like that. That's the different story. But interesting point here is that just your target philosophy can change your world so different. Like in the CISC time, your compiler was simpler, assembler was simpler, your hardware was really complex. In RISC world, your hardware is really simple. Like you see, CS147 DV is most philosophy is RISC. It's based on the MIPS instruction. MIPS is a RISC processor. Okay, so it's basically simplify the hardware, but it made the compiler assembler life complex. Like it's a complex implementation of the compiler and assembler. But in the software, it's an advantage of the software that we can go complex. We can actually implement more complex thing in the software side than hardware side. Hardware complexity goes up. It has a different problem. If some bugs comes in the hardware level, it's very hard to debug and so on and so forth. So we tend to kind of push it to the software world to make more complex feature there. So characteristics of the CISC now. One is definitely, as you probably can guess, memory access is directly available for most type of the instruction. Even an add can have embedded operand as a memory address. So go to the memory address, pick up those operands, and then just give me directly the result and store it back in the memory directly. And addressing modes are substantial in number. Like we just, like couple of slides back, we just reviewed only part of. They are not all type of. I just mentioned only top, like probably most popular type of addressing mode, but there can be many different other addressing modes as well. So CISC tend to support all of them because it just trying to make sure you're optimizing your memory usage, and your compiler is not that complex. You just have all sort of complex instruction right in the hardware. And variable length instruction format, we talked about that. And instruction includes elementary and complex operations. So of course it has the elementary operations like addition, subtraction. It can have complex operation like, okay, go and do matrix multiplication. Okay, this is my start of the matrix and it has this many element. These are the two matrix. Go and multiply that matrix and give me the result in this memory location. That kind of complex operations can be a part of the CISC, but not a part of the RISC. They are to be implemented through software library with the elementary instructions. Now RISC, data manipulations and instruction are strictly registered to register. Only two instructions can access the memory, load word and store word. Addressing modes are kind of limited to keep the circuit simple. So it's immediate addressing mode, registers type addressing mode, and displacement in case of load word, store word, that instruction, only few. Equal length instruction format, it's assumed that all the instruction of the same length, even if I use the bits or not use the bits, doesn't matter. It has to be 32-bit. And includes only elementary operations. We have only like less than 50 operations, and that's a almost full-fledged processor, right? CS147 TV. If you look at the MIPS, for example, as a RISC style processor, its instruction set is probably less than 100 different instructions. They're all elementaries. It includes, I'm including the floating point operations as well in the floating point processor. If we don't include floating point operation, it will be much less than 100, right? So this is very limited operation. So it heavily rely on the software libraries to implement complex functions. So hardware supports simple elementary operation that keeps the hardware simple, and which in turns make the processor really fast. Even it increases number of elementary operations to support complex instructions. So CISC to RISC, like when from 80s and the 90s, when people shifted from these two, it's a paradigm shift in the computer architecture. It's almost like analogous to shift from assembly language to the higher level language. Believe me or not, like back in like 70s, 60s, even before that, people used to program on assembly language. There is no high level language support like GC, Java, etc., right? So people used to do assembly language programming, and that's one of the reason assembly language was made so complex. Like that's a CISC philosophy as well. Like you are putting more complex instructions there, so that you can just type in less while you are programming. Whereas once this high level program came in, like C++, right, or Java, or like nowadays Python, that scripting language though, or Scala, right, that kind of things came up, then people don't use assembly language anymore. It actually much easier to program or describe your intent through high level language, much easier, right? So that's a programming paradigm shift from assembly language to the higher level language. Is analogous to that shifting when people switched from CISC mentality to the RISC mentality. RISC offers simplicity of the circuit structure, better performance through pipelining. That would be our next series of lectures on the pipeline. Basically, how we can not only pipeline, but in general, how we can improve performance of the processor. Okay. And also memory is no longer a scarce resource, hence RISC style does not suffer much from side effect of consuming more memory for the program code, which is now true for the handled devices as well. So people can well go with some mixed style of architecture, CISC and RISC, those philosophy, and people are going with that. So that's all for this lecture 12. If you have any question, send me email or ask me in the class.